welcome. Nice to be with you. As you learned in Module 7, adipose is really important for your body for a number of different reasons. First, your body stores extra energy in adipose tissue. This isn't the energy that you immediately rely on, as it takes a bit of time to convert this to usable energy, but it is a really important store. Additionally, adipose tissue is essential for thermoregulation, for retaining body heat. For warm-blooded animals, that is no small thing. For example, polar bears. Polar bears live in the Arctic, where the average winter temperature is minus 30 degrees Fahrenheit or negative 34 degrees Celsius. Part of how they stay warm is their adipose tissue. Polar bears can have fat reserves that account for half of their total body mass. Now, they can attain this impressive amount of adipose because they have a diet high in fat content. They eat the blubber of marine mammals, for example. And FYI, polar bear milk is about 30% fat. But adipose tissue does other things as well. All of your organs and nerves are cushioned by adipose tissue. So when you walk, run, jump, thank your adipose tissue for protecting those other organs from damage. We've already talked about the different types of adipose tissue: white, beige, and brown, and of course, pink adipose that isn't shown in this figure. The major characteristic of all of these different adipose cell types, the characteristic that they have in common, is the presence of lipid droplets. In brown adipose, the lipid droplets are numerous and small and intermixed with a lot of mitochondria. And remember, mitochondria are essential to producing the energy a cell needs to do its thing. And as you might surmise from the presence of many mitochondria in brown adipose, these cells work particularly hard in producing body heat. White adipose has one lipid droplet rather than many smaller ones, and the beige adipocytes are in between the white and the brown adipose cells. We are going to focus now on those lipid droplets. What are they made out of? Lipid droplets, are of course made up of lipids. One of the unifying characteristics of lipids is their inability to mix with water. The scientific term for this is hydrophobic. Lipids are all hydrophobic. When I mentioned earlier that using the energy stored in adipose tissue isn't an instantaneous thing, it takes a little while to convert lipids to energy because they are not water soluble. So the unifying characteristic of lipids is their inability to mix with water. They are hydrophobic. All fats are hydrophobic because of their similar chemical structure, a chain of carbon atoms bonded to hydrogen atoms. Now, the different types of lipids vary in the length and the shape of the carbon chain and the number of hydrogen atoms connected to the carbon atoms. Slight differences in this structure lead to big differences in the form of the fat molecule, and consequently, differences in how they work. Now, the basic types of lipids include triglycerides, phospholipids, steroids, and wax. Now, the most common lipid is the triglyceride. This type of lipid is mainly stored in adipocytes, the cells that make up your adipose tissue. A triglyceride consists of one glycol molecule with 3 fatty acids attached to it. The term fat molecule, it generally refers to triglycerides. So I use the term fat as a synonym for triglyceride. This is also why I try to always refer to adipose tissue not as fat, but rather as adipose, because fat is the term for the molecules inside the adipocytes that store energy. Now, phospholipids are another really important type of lipid. Now, the structure, sorry, my animation's a little funny right here, but the structure of these lipids consists of a head that is attracted to water. So again, we call this being hydrophilic as opposed to hydrophobic. So they have a head that is attracted to water, that's hydrophilic, and a tail of usually 2 fatty acids that is hydrophobic. The hydrophilic heads point away from each other, and the hydrophobic tails point towards each other. This arrangement, it keeps water on one side from intermixing with water on the other side of the layer. Now, without this lipid bilayer, there wouldn't be any cells, as this is how the barrier around a cell is made. I'm going to do my funny animation here again. Sorry about that. So, steroids are a large group of lipids derived from cholesterols. You're likely familiar with steroid hormones like testosterone and estrogen. We'll talk about them in a later module. Now, this type of lipid, steroids, is really different from fatty acids. So fatty acids have bonds that can rotate, and steroids are rigid. And then there are waxes as well. Now, we are going to focus our attention on the triglycerides. Remember, a triglyceride, or a fat molecule, is a glycerol molecule with 3 fatty acids attached. There is a lot of variation that can exist in the types of fatty acids. And this variation in fatty acids is where our investigation of human variation is going to go next. Let's start with the basics, though. What are fatty acids? So fatty acids are the building blocks of the lipids in your body. To reiterate, you need fat molecules because they provide energy for the body when glucose isn't available. They absorb fat-soluble vitamins like A, D, E, and K. They make hormones and cell membranes, and they insulate all of the nervous system tissues. So fat is not a bad thing. Don't be afraid of eating fat. You just pay attention to what kind of fat you consume. There are 3 major types of fatty acids. So the major types of fatty acids: saturated, unsaturated, and trans fats. Saturated fats are solid at room temperature. So the saturated term refers to the number of hydrogen atoms surrounding each carbon atom. I'll show you a picture of this in just a minute. Unsaturated fats are liquid at room temperature because they have fewer hydrogen atoms bonded, not atom bombs. They have fewer hydrogen atoms bonded to their carbon chains. Trans fats are vegetable oils that have been industrially hydrogenated so that they remain solid at room temperature. So for example, the partially hydrogenated oils. Okay, let's take a look at what fatty acids look like to help these make sense in your mind. On this diagram of a fatty acid, I want to draw your attention to the long hydrocarbon chain that gives the fatty acid its tail-like structure. So fatty acids have between 4 and 24 carbon atoms in this chain. The fatty acid you see here is defined as a saturated fatty acid because all the carbons are connected to each other by just one bond, and they have hydrogen atoms all around. As a consequence of this structure, the fatty acid is configured as a straight line, and the straight tails, as I like to think of them, enable them to form a solid structure at room temperature. Let's compare that to other versions of fatty acids. In this unsaturated fatty acid, you see that some of those carbon atoms have double bonds between them. These double bonds make the chain bend. So the more double bonds, the more bent the fatty acid, and the more bent the fatty acid, the less its ability to be solid at room temperature. So unsaturated fatty acids have some double bonds between carbon atoms, which make them bend. The more double bonds, the more bent the fatty acid. Now, let's look at a trans fatty acid. Now, this type of fatty acid does not occur in nature. We make them through the process of hydrogenation. Now, as shown in this figure in the bottom of the frame, the hydrogen atoms, they line up oddly so that the double bonds between the carbon atoms orient in a straight line. And that straight line configuration is what makes these fatty acids form a solid at room temperature. Now, the fatty acids that are drawn here are drawn in a line, but we're going to see some in a few minutes, in a couple of moments, that show you how they bend at those double bonds. So ignore the fact that they're straight for here. You'll get to see that bending structure in just a moment. But from a dietary health perspective, you need to consume fats. And just remember that healthy fats are generally liquid at room temperature, or are known to be from an animal. Trans fats make yummy foods, but that odd linear shape to the tail, it makes them unhealthy once they're inside your body. Now, there's a lot of disagreement over the healthiness of saturated fats, i.e., is it healthy to eat meat? Now, one of the things that to keep in mind about humans is that we're generalists. So think back to Ardipithecus and Australopithecus, and especially that transition to Australopithecus. With that genus, there was an expansion of dietary niche. This expanded even more with genus Homo. As we moved into a vast array of different climates and environments, our ability to eat lots of different foods is what made that possible. There aren't hard and fast rules about the best or most healthy way to be a human. Now, one meta-analysis of 21 studies said that there was not enough evidence to conclude that saturated fat increases the risk of heart disease, but when saturated fat is replaced with polyunsaturated fat, that might reduce the risk of heart disease. Okay, so another distinction that we need to talk about is between monounsaturated fat and polyunsaturated fat. Okay, now you're going to start to get to see those bends with the double carbon bonds. Now, the scientific abbreviation the scientific abbreviations that you're seeing here are the C for carbons and the H for hydrogen, and we have that carbon tail or the carbon chain and the hydrogens all around it, as you can see at the top with the saturated fatty acid. In the middle, I have the unsaturated fatty acid, and here they are demonstrating that bend with that double bond, that carbon double bond. And then that trans fatty acid, you can see the double bond and there's a slight offset, but it's still fundamentally a straight carbon chain despite that double bond. So the only way to get that straight configuration despite the double bond is through that industrialized hydrogenation. So let's think now about the saturated, monounsaturated, and polyunsaturated. So here we have saturated fatty acids at the top. And again, remember, these are the ones that have the carbon chain and the hydrogen single bonds between all of the carbons and then hydrogen atoms all around. Now the monounsaturated fatty acids, you can see here. And here you have just one bend. Oleic acid is a really nice example of this. And now I want to introduce you to polyunsaturated fatty acids. Here's two examples, AA and LA, so linoleic acid. These are the polyunsaturated fatty acids that are also called omega-6 fatty acids. And then you have the N3 polyunsaturated fatty acids here, so EPA, DHA, and ALA. Now, these polyunsaturated fatty acids are the ones we're going to really focus our conversation on from here on out. So those N6 and the N3. So the N6 and N3 are also interchangeably referred to as omega-6 and omega-3. And I want to explain how they differ from each other. So if you look at the end of these, so go to the end of the carbon chain, and hopefully you can see my cursor here. And if you count back from the end, 1, 2, 3, 4, 5, 6, you go 6 carbons in from the end of the tail, and that's where you get that first double bond. So that's an omega-6 polyunsaturated fatty acid, and it's 3 of those, 1, 2, and 3 for the omega-3 polyunsaturated fatty acids. So that's the big defining difference between those two types of polyunsaturated fatty acids. So now let's think a little bit more about what the difference is between these two. So there are two main types of polyunsaturated fatty acids. So these are also referred to in a shorthand called PUFAs, which always makes me laugh. So PUFAs, and I'll try not to laugh while I do the rest of this video. There are two main types of PUFAs, omega-6 and omega-3. A few minutes ago I mentioned in passing that the carbon chain of a PUFA is between 4 and 24 carbons long. The ones with less than 6 carbons are referred to as short-chain PUFAs, and the ones with more than 12 are long-chain PUFAs, and the ones in the middle, yep, those are called medium-chain fatty acids or medium-chain PUFAs. A really important thing about PUFAs, and one of the reasons you hear about these in conversations about healthy diets, is that our bodies can make saturated and monounsaturated fatty acids, but we can't make polyunsaturated fatty acids. This is why PUFAs are essential dietary nutrients. You have to get them from the foods you eat. So let's take a break here, let all of that sink in, and then we'll pick up the science with something pretty cool that our bodies can do with the short-chain polyunsaturated fatty acids that we eat. This is where the human variation comes into the story.